Hello, we are going to discuss the language of hypothesis testing. A hypothesis is a claim or statement about a characteristic of one or more populations. The test is a procedure based on sample evidence and probability used to test claims about a characteristic of one or more populations. So, because we are using sample data to test a claim, we cannot say with 100% certainty that the statement is true. All we can determine is if the sample data either supports the claim or does not support the claim. Now, there's some interesting symbols here. We need to work with those. So HO and H1 are symbols. You can use that either with the mu, the mean, or the P, population. With either mu, mean, or P, proportion. The null hypothesis is a statement that the value of a population parameter, either mean or proportion, is equal to the value. Okay, so HO always has equal sign. Okay, there will be no inequality in the HO. So the alternative hypothesis, which is H1, has the inequalities not equal to, greater than, or less than. So let's review. This means not equal to. This is going to be a two-tailed test. Okay? This symbol is greater than. And this symbol is less than. So we have one tail and two tails test. So a two-tailed test occurs with a not equal to symbol. Left tail is less than, and a right tail is greater than. So that means the alpha is either going to be in the two tails, left tail, or right tail. So each time we are going to draw a picture. So let's see, how do we write these up? Let's practice just basic writing. Identify HO and H1. Then determine if the test is left-tailed, right-tailed, or two-tailed. So what we want to do is decide what it is, and then we'll draw a picture to help us decide if it's left-tailed, right-tailed, or two tails. Okay, less than. So we know it's going to be either left or right. So our H1 that's a percent, which is a proportion. P is less than 0.40. Now, the HO is always equal, so P equals 0.40. So if we draw a picture, where does less than end up? So I'm going to say that my area here, my alpha is 0.40. Okay, so that's going to be a left tail test. So notice that less than is going to go left. Okay, the mean, here's mean, different symbol, amount of water in a bathtub is more than 124 gallons. So we want more than 124 gallons. So that means mu is greater than 124, or mu is equal to 124. Okay, and we will shade and decide which tail it is. Right tail, left tail, or two tails. So here's your 124. So greater than 124, because it's a mean or an average, is going to be a right tail test. Okay, determine the alpha level. Determine the critical value. And the critical value was the z-score or t-score, depending on what distribution it is. Alpha is the probability of making a type 1 error. The critical value separates the critical region from the values of the test statistics that do not lead to a rejection. So we are going to either reject or do not reject the claim. Remember, we cannot prove with 100% confidence because we're taking samples. So the critical region, also known as the rejection region, is a set of values of the test statistic that will cause us to reject HO. For two-tailed, you must split it evenly into two tails. So we're going to go ahead and draw a picture and see what that would look like. So you're going to have two critical values. We're going to call them CVs. The area would be here and here. So if you notice, like your alpha, how you have plus or minus, that's two values. A left tail means all of the alpha goes into the left tail. And again, here's your critical value. We'll put CV for critical value. And it shades to the left. And the shaded region is called the rejection region. So this is the rejection region. Okay, each time. So therefore, if your values fall in this area, you reject. If it falls in the middle there where it's not shaded, you do not reject. Okay, then the right tail test, all of the alpha goes into the right tail. Again, we have a critical value. And once again, the rejection region is to the right. Okay, so your z values are used in proportions only. So we wanted to find a critical z value here. So we will practice. So we have a two-tailed alpha equal 0.01. So let me go to the next page here. And it seems as if we're cut off a little bit. Let's go back. There it is. Okay. So on a two-tailed alpha equals 0.01, you're going to have two values. So you've got to have alpha divided by 2. If it's two-tailed, you will always divide by 2. If it's a one-tailed, you will not divide by 2. So we can either, well, this is not up there. So we're going to do an inverse norm of 0.0050 0, and 1. And because we're using the standard normal curve, we can just go ahead and, once we get the one answer, we can get the other answer. So we're going to do second vars, inverse norm, 0.0050 0, and 1. I'm going to do it left tail. I get negative 0.2575. And again, for our purposes, we usually do z-scores too, but these are given generally to 3. So we're going to say, to be consistent, our z-scores would be z is equal to, we could do plus or minus, or write them separately, 2.58, because the 5 rounds out. Now, if you have a right-tailed test, okay, where's the right tail? Appears to the right. This is all of 0.05. That whole area there is 0.05. Here we had to split it up. So you're going to do inverse norm, and remember, it's area to the left, so you have to do 0.95, 0, and 1. The inverse norm always gives you area to the left. Giving us 1.64. So our critical value is z is equal to 1.64. So let's box that. So again, we want to remember the z values are for the population proportion. Okay, now I know we have some formulas here. And we will be using our calculator to find our test statistics. So the test statistic is the value computed from the sample data used to make the decision about whether or not to reject HO. So for proportion, it's Z. So proportion is a Z score. And notice that a mean is a t-score. We want to draw the appropriate graph and label the test statistic. Okay, so that's one thing. It's really important that we can draw pictures here. We'll do that here. Calculate and state the p-value. This comes from the calculator. The p-value is the probability of getting a value for the test statistic that it is as least as extreme as the one found in the sample data, assuming HO is true. So small p-values, less than alpha, mean the results are unusual and there's significant difference from HO you reject. So we're going to say if p is less than alpha, reject HO. Okay. If p is greater than or equal to alpha, you do not reject HO. Actually, we're going to say greater than because I do not know right away of a condition where it would be less than. Okay, so we have the classical approach, which is if the test statistic falls in the critical region, we reject HO. If it does not fall in the critical region, do not reject HO. And then you also have the p-value approach. If p is less than alpha, reject. P is greater than alpha, we do not reject. So we'll be looking at both ways to decide if we reject or do not reject. Okay, writing the final conclusion. Okay, so reject HO. Again, it's kind of like the interval. I am blank % confident of blank that the true mean is between blank and blank. So we're going to say this. There is sufficient evidence to conclude that if you reject it. So if reject is a positive, there is. You see, do not reject is not. So the nots go together and the rejects go with is. Claim. The proportion of women who smoke is less than 0.35. Conclusion, reject HO. So we're going to say there is sufficient evidence to conclude. So if we reject, we always start here. That. Okay, now we restate the claim. The proportion of women who smoke is less than 0.35. Okay, number 2. Claim. The mean number of peanuts in an 8-ounce jar is not 200. Do not reject. There is not sufficient evidence to conclude that the mean number of peanuts in an 8-ounce jar is not 200. So notice if we reject HO, do not reject HO. So there is not sufficient evidence to conclude that the mean number of peanuts in the jar is not 200. So the picture would look like this on the first one, that the proportion is less than. So we would draw and shade to the left. And so the not is a not equal to. So the not gives us, in the original statement, a two-tailed test. If under a given assumption, the probability of an observed event is exceptionally small, which is unlikely, we say that the result is statistically significant. When results are found to be statistically significant, we have evidence to reject the null hypothesis. So we're going to look at that in a little bit, okay? Okay, so let's just look at our errors. Okay, you have a type 1 and a type 2 error. Type 1 error occurs when you reject HO when it's actually true. That's your alpha. And type 2 error occurs when you fail to reject HO when HO is actually true. So that's known as beta. So the defendant is innocent. This defendant is guilty. You reject HO when it is true. So an innocent person goes to jail because you're saying you're going to reject that they're innocent. So that means an innocent person goes to jail. Notice we didn't say that they're guilty. Okay, so basically, non-innocent does not mean that they're guilty. And you see that a lot of times in the court of law. Type 2, do not reject HO when when H1 is true. So the person is guilty, but we do not reject it. So the guilty person goes free. Okay, so let's determine the type 1 and type 2 errors below. So a reporter claims that more than 50% of workers find their job through networking. So HO it's a percent. So P is equal to 0.50. Remember, your HO is always equal. So more than, P is greater than 0.50. So again, looking would look like this. So if you reject HO when H1 is true, we're going to reject P equals 0.50 when P equals 0.50 is true. If you do not reject, you did not reject P equals 0.50 when P is greater than 0.50. A sociologist claims that the average age when teenagers begin working is less than 15. Okay, so we have mu is equal to 15. Mu is less than 15. So again, what would that look like? Reject HO when HO is true. You're going to reject mu equal 15 when mu equals 15 is true. And here we do not reject. Mu equals 15 when mu less than 15 is true. Oh, not less than. This would be when mu equals 15. Let me correct that. Okay. So what we want to do is just go over the appropriate decision again. So if the test statistic falls in the critical region, we reject HO. If the test statistic does not fall in the critical region, do not reject HO. If the p-value is less than alpha, we reject HO. And the p-value greater than alpha, you do not reject HO. And so to write your conclusion, addressing the original claim, there is sufficient evidence to conclude and then restate the claim, or If you do not reject, there is not sufficient evidence to conclude that and restate the claim. So we will see how to do these here, how to write out our conclusions, how to write out a hypothesis test next class. Have a good day.